Hello students, today we start new chapter, that is kinematics of rigid bodies. In this chapter, we cover the problems of uh, objects with dimensions but without forces. In previous two chapters, we covered the problems of kinematics of particles, that is, we covered the problems of objects without dimensions and without considering the forces causing motion. In this chapter, the difference will come, will be that dimension the object will come into consideration. So here we are going to consider the motion of the objects with the dimensions, but still without considering the forces causing the motion. Motion of the rigid bodies is of three types: translation, rotation, and general plane motion. First, let us understand what is translation. Translation is nothing but, students, it's something like what is the rectilinear motion, what we have covered in the previous chapters of dynamics. All right, but as in the previous chapter we considered the motion, rectilinear motion of the objects without dimension. Here in this part we cover the rectilinear motion of the objects with dimension. To identify the translatory motion, a rigid body is said to have translatory motion if we draw some imaginary line on the body which remains during the entire motion, it remains parallel to its original position. So this is the identification of translatory motion of the rigid body. All right, what are the examples? Motion of the car moving along the straight road, motion of the train along the straight road, motion of the lift, etc. So translatory motion concepts of a rigid body are almost same as that of rectilinear motion. All right, and only the difference comes that size of the object is taken into consideration. Here we have shown a diagram where you can see that this is the body. It is in translating motion. This is the imaginary line A1, B1 we have drawn. During this entire motion, it's remained parallel to its original position, right? Next comes to rotation. In this case, the particles of the rigid body move into the concentric circular path. The common center of rotation, common center of circles may lie on the body or may lie outside the body. Can you see that? First, very important thing that the body in the we say that rotation of the rigid body, that means the body is rotating about the fixed axis of rotation. Axis of rotation or center rotation may lie on the body or may lie outside the body. Like in this case, first example, can you see that? C is the center of rotation of the concentric circles. Can you see that is a fixed axis rotation? There is a particle A1, A and B. So they are moving along the concentric circular paths having center C. In the second case, you can see that center rotation is lying outside the body. In this case, the two particles A and B are moving along the circular path like this, having common center C. So all particles on the body in rotation will be moving along the concentric circular paths. That means having common center. In this case, the body rotates about the fixed axis, which we are going to discuss at length later in the chapter. Next, we come to what are the examples of rotation about fixed axis. These are some of the examples: motion of the flywheel, motion of the giant wheel, what we enjoy in the fairs and amusement parks and all, and motion of the doors. Motion of the doors we all have seen at the home. Doors rotates about the fixed axis passing through the hinges. Third type of motion is general plane motion. General plane motion is summation of translation and rotation. So any motion which is combination of translatory motion, rotary motion is called as general plane motion. Examples: motion of the wheels of the automobiles, right? You consider the motion of the car moving along the road. So it is the wheels of the automobiles will have not only translatory motion, they translate also along the road. At the same time, wheels rotate also. This is the example of general plane motion. Another example, motion of the ball in all the sports, whether it is cricket, football, volleyball, basketball, in all the games, ball not only rotates, but it translates also. Another example is motion of yo-yo. Most of us have enjoyed yo-yo, right? So yo-yo is what? Basically, it is a disc, right, around which a string is wrapped. And in one action, when you throw it, that string, the disc will go away from you. And at the same time, the string is unwinding from the disc. When you pull it towards you, then there will be winding of the string on the disc, and it comes closer to you. So it has the rotary component also. It has the translatory component also. Now, students, Translatory motion, we are not going to discuss, as in our examination, they don't ask any problem of translatory motion of rigid bodies because it is almost same as that of rectilinear motion of the particles. But yes, rotation we have to discuss at length. So now we are going to consider rotation about fixed axis. As I told you that the bodies which rotate about fixed axis, they are called as, it is called as rotation. Now here we have considered a body or a rigid slab which is rotating about O, which is rotating about O. All right, there is a point or a particle P, which initially is at point P dash. After some time T, it reaches a point P. So that the particle P is moving along the circular path for which center rotation is O. So the linear displacement covered along the circular path by the particle is S. Angular displacement during this journey during this rotation about O is theta. R is the radial distance. So in this case, what is axis rotation? Axis rotation is the line or axis perpendicular to the plane of the body and passing through the point, passing through the center of rotation. So that is called as axis of rotation. Now here let's understand the terms. Theta is angular displacement or position of the body. Omega is angular velocity of the body. Alpha is angular acceleration of the body. R is the radial distance of the point P from the axis of rotation O through O. S is the linear displacement of point P on the body. B is the velocity of the point P on the body. AT is tangential acceleration of the point P on the body. N is normal acceleration of the point P on the body. Rotary motion about fixed axis may be of three types. It can be at constant angular acceleration. It can be at constant angular velocity. It can be at varying acceleration also. Now, if you look at the same diagram I have represented here again, we have shown point P on the body, right? We understand that body is rotating in anti-clockwise direction about axis of rotation through O. Omega have shown angular velocity, alpha have shown AN. See, we should also understand that theta, omega, and alpha refer to the body in rotation. Theta, alpha, and omega refer to the body in rotation, whereas AN, AT, and V, normal acceleration, tangential acceleration, and velocity, refer to a point on the body. Like in this example, this diagram, velocity, AT, AN refer to the point P on the body, which is rotating about a point O or axis of rotation through. Now we'll understand different types of the rotary motion. Now, first we consider rotary motion at constant angular acceleration. As students, there are three equations of motion of rectilinear motion at constant acceleration. V is equal to U plus AT, S is equal to UT plus half AT square, V square is equal to U square plus 2S. On identical lines, here are three equations of rotary motion are there at constant. When the rotary motion is at constant angular acceleration, we can use three equations of motion. The first one is omega is equal to omega naught plus alpha t. Second one, theta is equal to omega naught t plus half alpha t square. Third one is omega square is equal to omega naught square plus 2 alpha theta, where omega naught is initial angular velocity, omega is final angular velocity, alpha is angular acceleration, theta is angular displacement of the body, t is the time. If rotary motion is at constant angular velocity, then there is only one equation. What is that? Angular velocity is angular displacement upon time, or angular displacement is angular velocity into time. Third type of motion which we come across as in rectilinear motion is rotary motion at varying angular acceleration. Again, concepts here are very much identical to what we learned for rectilinear motion at varying acceleration. Over there, it was v is equal to ds by dt. Here it is omega is equal to d theta by dt. D theta is the omega is angular velocity. Rate of change of angular displacement at any instant gives you angular velocity at that instant. Then angular acceleration alpha is equal to d omega by dt. So rate of change of angular velocity with time at any instant gives you angular acceleration at that instant. Alpha is equal to d omega by dt. If you multiply by d theta, divide by d theta, so then d omega by dt becomes omega. So it gets reduced to this form. So students, we come across one formula is alpha is equal to d omega by dt. Another is alpha is equal to omega d omega by d theta. So depending upon, as over there, three types of problems were there. Here also we have three types of the problems in varying acceleration will be there. If alpha is function of time, then we use d omega by dt to get omega t relation. If alpha is function of theta, We use omega d omega by d theta and get omega theta relation. And if alpha is function of omega, we can write it equal to d omega by dt to get omega t relation. We can write it equal to omega d omega by theta to get omega theta relation. So three types of the problems will occur in varying acceleration problems. Now let's come to relation between linear and angular velocity. As in the diagram what we just now discussed, that S is the angular linear displacement of the particle P along the curved path. R is radial distance, so S is equal to R theta. If you differentiate with respect to d, ds by dt is equal to r d theta by t. ds by dt is v, d theta by dt is omega. So v is equal to r omega. We know that at is equal to dv by dt. So d by dt is r omega. So r d omega by dt, that is r omega. An is v square upon r, v is r omega. So an is equal to r omega square. Students, motion diagrams can also be drawn for rotary motion at constant acceleration or at varying acceleration or at constant angular velocity. What kind of the motion diagrams we draw for rotary motion? Theta t, omega t, and alpha t. All right. For solving these problems, we need to remember that certain concepts which are again identical to the motion diagram problems of rectilinear motion, which we have covered in the first chapter of dynamics. Now, slope of theta d diagram at any instant gives angular velocity at that instant. Slope of angular displacement time diagram at any instant gives you angular velocity. Similarly, next we come to slope of omega t diagram at any instant gives you angular acceleration. Area under omega t diagram for a particular time interval gives you change in angular displacement for that time interval. Area under alpha t diagram for a particular time interval gives you change in angular velocity for that time. So these are the basic fundamental concepts or theory part of rotary motion about fixed axis or rotation about fixed axis. So let's start solving the problems on rotation. My first problem. A speed of rotor decreases uniformly from 2000 rpm to rest in 300 seconds. Determine the angular deceleration and the number of radius before coming to rest. Omega is initial angular velocity 2000 rpm. Students, here at the bottom I have given note for unit conversion. See, we know that one revolution is equal to 2 pi radians. So 1 radian, see, revolutions are to be converted into radians, you multiply by 2 pi. If 1 revolution is 2 pi radians, then 1 radian is equal to 1 by 2 pi revolutions. Similarly, we understand 1 rpm is equal to 2 pi by 60 radian per second. Why? Each revolution is equal to 2 pi radians. Minute is equal to 60 seconds. So 1 revolution per minute is equal to 2 pi by 60 radian per second. So 1 radian per second will be 60 upon 2 pi. So in short, what you need to remember that if you want to convert revolutions into radians, multiply by 2 pi. If you want to convert radians into revolution, divide by 2 pi. Similarly, remember that if RPM are to be converted into radian per second, multiply by 2 pi by 60. And if radian per second is to be converted into RPM, you have to multiply by 60 upon 2 pi. So this unit conversion, what I have shown here, should be remembered. Now, here, initial angular velocity is given 2000 RPM. Let's convert into radian per second by multiplying with 2 pi by 60. It comes to 209.4. Final angular velocity is 0, t is 300. Now, selection of the equation is absolutely in the same manner. As over there, V and T are into consideration, we were preferring what? V is equal to U plus AT. Here, omega and T are into consideration, we prefer omega is equal to omega naught plus alpha T. As omega is into consideration and T. So omega is equal to omega naught plus alpha T. Omega is 0, omega naught is given, alpha is unknown, into T is 300. You got alpha. Alpha is minus 0.698 radian per second square. That means it is not, it is under angular deceleration. So angular deceleration of this motion is 0.698 radian per second square. Now you want to find the angular displacement. Again, so if omega and theta are into consideration, then we prefer to use omega square is equal to omega naught square plus 2 alpha theta. Now, final angular velocity omega is 0, omega naught is 209.44. Alpha is minus 0.698 into theta. So theta is obtained as 31422 radians. All right. So this is what is asked in the sum. So simply we applied the equations of motion for rotation at constant acceleration. Second problem. A wheel is attached to a shaft of an electric motor of rated speed of 1740 RPM. When power is turned on, unit attains the rated speed in 5 seconds. That means from start to this speed, it takes 5 seconds. When the power is turned off, then unit comes to rest in 90 seconds. That means from this speed to rest, it takes 90 seconds, right? Assume uniform acceleration. Determine the number of revolutions the unit turns second to attain that rated speed and second to come to rest. Now, students, first we'll take accelerating motion. Accelerating motion means it starts from rest. Final angular velocity is 1740 RPM. So we'll convert into radian per second. 1740 into 2 pi by 60. It comes out to 182.21 radian per second. Time is given 5 seconds. It takes 5 seconds to reach that rated speed. Again, omega and t are into consideration. So I'll use omega is equal to omega naught plus alpha. Put the value of omega. Omega naught is 0. Put the value of t. You get alpha is 36.44 radian per second square. You want to find theta. As omega and theta are into consideration, you will use the equation omega square is equal to omega naught square plus 2 alpha theta. Substitute the value of omega naught 0. Substitute the value of alpha as well, and then you get the value of theta. Theta comes out to be 455.55 radians. So that comes out to be divided by 2 pi to convert into revolution, because he's asking answer in revolution. So we have to, you cannot leave the answer in radians. You need to divide by 2 pi. You get it in revolution. Now let's come to decelerating motion. Initial angular velocity is 182.21 radian per second. Final angular velocity is 0. Time is 90 seconds. Omega is equal to omega naught plus alpha t. Final velocity is 0. Initial angular velocity is 182.21. Time is 90 seconds. So alpha this time comes out to be minus 2.025 radian per second square. Now, next we want to find theta. As omega and theta are into consideration, we should use omega square is equal to omega naught square plus 2 alpha theta. Put the value of omega, that is 0. Omega naught is 182.21. Alpha is minus 2.025 and into theta. So theta comes out to be again in radians, that is 8197.65 radians. You want to find in revolution, divide by 2. You get it 1304.7 revolutions. All right. So it turns by this many 72.5 revolutions to attain the rated speed from rest. And from rated speed to rest, it takes 90 seconds and it turns 1304.7 revolutions. Basically, in these two problems, we have understood how to apply equations of motion for constant acceleration rotary motion. Next problem is also based on equations of motion only. Let's read the sum. Problem number 3. In the manufacture of constant angular acceleration electric motors, that means motion is at constant angular acceleration. Motors for special application requirement is that regular acceleration should not deviate more than 1% from the nominal design value of alpha is equal to 80 radian per second square. Each motor coming off the assembly line is individually tested to meet the requirement. If each unit is started and run exactly 5 seconds, find the acceptable range of angular velocity in revolutions per minute. See that he's asking the range of angular velocity in RPM units, not in radian per second, that the motor should have at the end of this time interval. Find the corresponding range of angular displacement during this time interval. Now, he is given that nominal design value of alpha is 80 radian per second square. He says that 1% deviation is allowed, 1% plus and 1% minus. First, I have taken 1% plus. So 80 plus 1 by 100 into 80, 80.8 radian per second square. If I reduce 1%, 80 minus 1 by 100 into 80, 79.2 radian per second square. Now, in the first case, it starts from rest. It takes 5 seconds. So we want to find what is the velocity, angular velocity after 5 seconds. So we use omega is equal to omega naught plus alpha t. I've called it omega 1. Omega naught is 0, 80.8 into 5404 radian per second. You want to find this value in RPM, so multiply by 60 upon 2 pi. This comes 3857.9. In the second case, alpha is 79.2, so we'll get the corresponding angular velocity at the end of 5 seconds. Omega is equal to omega naught plus alpha t. All right, omega naught is equal to 0 plus 79.2 into 5, that is 396 radian per second. Now convert it into RPM, multiply by 60, divide by 2 pi, 3781.52. So what we can say that what is asking range of the angular velocity if 1% deviation of angular acceleration allowed. So range of the angular velocity will be 3781.52 rpm to 3857.91 rpm. He is asking corresponding range of total angular displacement. So we will here final angular velocity is not into consideration. So we will use theta is equal to omega naught t plus half alpha t square. So in first case, theta 1 is equal to omega naught is 0 plus half into 80.8 into 5 square 10108. In the second case, theta 2 is equal to omega naught t plus half alpha 2 t square. Omega naught is 0 plus half into 79.2 into 5 square 998. Hence, the range of the angular displacement is 990 to 1010 radians. Okay, let's move to the next sum. Next, I read that. At the end of 20 seconds, a flywheel reaches a speed of 15 radian per second starting from rest. That means what is given here? Omega naught is 0, omega is 15 radian per second, and t is 20 seconds. If the angular acceleration is uniform, find the angular displacement during 16th second, not 16. We have recorded omega naught is 0, omega is 15 radian per second, t is time 20 seconds. He's asking displacement during 16 seconds. So what we'll do that? We'll calculate the displacement during 16 seconds. We'll calculate the displacement during 15 seconds and we'll take the difference. We'll take the difference and that gets you the angular displacement during 16 seconds. Now, let's use the equation as omega and t are into consideration. Omega is equal to omega naught plus alpha t. Omega is 15, omega naught is 0 plus alpha into 20, that is 0.65 meter radian per second square. Then theta is equal to omega naught t plus half alpha t square. We get theta in 16 seconds 0, omega naught is 0 plus half into 0.75 into 16 square, that comes 96 radian. We then get angular displacement in 15 seconds, that is 0 plus half, omega naught is 0, half into alpha into 15 square, 84.375. So angular displacement during 16 seconds will be theta 16 minus theta 15. So this comes out to be 11.625. All right. Now let's take problem number 5, which will be solved by using motion diagram. All right. I'm reading the sum. A wheel accelerates uniformly from rest to a speed of 200 rpm in half second. What it says that it starts from rest and it runs a speed of 200 rpm in half second. It then rotates at that speed for 2 seconds. Right. During that 2 second period, this speed remains constant before decelerating to rest in 1/3 seconds. How many revolutions does it make during the entire time interval? Now, student, this problem is can be solved as analytical solution also. How you can solve it analytically? Motion is in 3 stages. First stage is of accelerating motion for half second. Second stage is constant angular velocity motion for 2 seconds. And third stage is for 1/3 second, right? That is decelerating motion. Now, you can solve this problem analytically also, but we have solved this problem using motion diagram. If you remember it, during our problems of motion diagram for rectilinear motion also, we had discussed if you want to attempt any problem through motion diagram and they have not asked you to draw any motion diagram, you should always attempt it through the middle diagram, that is VT diagram. So VT diagram in rectilinear motion means what? Omega T diagram in rotary motion. All right. So here I have drawn omega T diagram. Why I have decided to solve this problem by motion diagram, I'll tell you. He is asking angular displacement during the entire motion. It starts from rest, it comes to rest. So total area under omega T diagram will give you total angular displacement. All right. Now you can see that how omega T diagram has been drawn. Now you can see that we have drawn the axis for time on x-axis and omega in revolutions per second on y-axis. For 1.5 seconds, it is accelerating motion. Omega is accelerating at a constant rate. That means omega T diagram will have a linear variation. How long it goes on? Till it becomes 200 rpm. But here I have recorded is at 200/60 so that it becomes revolutions per second. You know why this conversion has been done? Because on x-axis we have time in second. So on y-axis, angular velocity should be in revolutions per second. Then for 2 seconds, angular velocity remains constant. So constant ordinate has been shown. Next for 1/3 seconds, it decelerates as a constant rate. right, and comes to rest. That means omega t diagram should have linear variation with negative slope. All right. Now we understand that it starts from rest and it comes to rest. All right. Omega t diagram is positive. So total area under omega t diagram will give you angular displacement. How will you get it? Now diagram has been drawn. What is area of this triangle? Half into base into half into base is 1 by 2. Height is 200 by 60. What is area of this rectangle? 2 into 200 by 60. What is area of this triangle? Half into 1 by 3 into 200 by 60. So that comes out to be 8.06 revolutions. Now, next two problems we will be considering for varying acceleration. Problems of rotary motion at varying acceleration. All right, we read it. Angular acceleration of a flywheel of diameter 0.6 meter rotating about its centroidal axis given by alpha is theta by 4. When I read and I come across alpha is theta by 4, it indicates that it is a problem of varying acceleration where alpha is function of theta, where theta is in radians. Determine the magnitude and velocity and magnitude of resultant acceleration of point on the rim of the flywheel at theta is equal to 2 radians. Well, students, for the problem, diameter is 0.6, so radius 0.3. Alpha is given theta by 4, which is, now if alpha is function of theta, we write it equal to omega d omega by d. Separate the terms of omega and theta. Integrating both sides, you get omega square by 2 is equal to theta square by 8 plus c1. Yeah, positive sign aa gaya galti se. It is not a positive sign. What it is, I hope you can understand. Omega square by 2 equal to theta square by 8 plus c1. This is a printing error. Now, as boundary conditions are not given, we have assumed that flywheel starts from rest. That means I have assumed that theta omega angular velocity is 0 at theta is equal to 0 as boundary conditions are not. If you put omega and theta 0, you get c1 as 0. So omega square is equal to theta square by 4 or omega is equal to theta by 2. At theta is equal to 2 radians, alpha is equal to 0.5 radian per second square and omega is equal to 1 radian per second. He is asking you to find the magnitude of velocity and magnitude resultant acceleration of a point on the rim of the flywheel, which is at a radial distance at radius of 0.3. This diagram was in fact not required to be drawn. Without drawing the diagram also, we could have found the velocity of a point on the rim and resultant acceleration. But I have drawn a diagram. It is for better understanding. I have taken a flywheel which is rotating about its centroidal axis. So we have shown the hinge. Hinge means what? It rotates. Hinge allows the body to rotate about it only. What is the property of the hinge? If you connect any body to the hinge, it will allow the body to rotate about hinge only. I'm assuming that it is rotating in clockwise direction. I marked a point P on the rim of the flywheel. Now, normal direction will be directed towards center of curvature. As it is turning in clockwise direction, this will be tangential direction. Along the tangent, you'll have tangential acceleration, you'll have velocity. Normal acceleration is directed towards center of curvature. Total acceleration will be resultant of A and P, right? So this diagram has been drawn assuming that flywheel rotates in clockwise direction and point P is marked as one of the point which is right at this point. We'll mark tangent and normal direction, then we mark AT, A and B and then resultant acceleration. Now students, first we calculate velocity of the point P. B is equal to R omega, R is 0.3, omega is 1.3 meter per second. AT is R alpha, R is 0.3, alpha is 0.5 or 0.15 meter per second square. AN is R omega square, R is 0.3, omega is 1, so 0.3 meter per second square. Now we want to find total acceleration. Total acceleration is AN square plus AT square, square root of that, right? Square root of, you have substitute the value AT, that is 0.15, AN is 0.3, substitute and find the resultant acceleration. Okay, let's move to the next sum. This problem is also problem is of varying acceleration only. The next two sums. Now we will take first question number 7. That's the question number 7. Short sum. A particle moves along a circle of radius 20 centimeters so that S is equal to 20 pi t square centimeter. Find its tangential and normal acceleration after it has completed a revolution. S is equal to 20 pi t square. V is equal to ds by dt. right? What is that? 40 pi t. At is dv by dt, that is 40 pi. At r is equal to 20 centimeter, s is 20 pi t square, and which is equal to 1 revolution. R is equal to 20 centimeter. It's just 5, it is written with it is centimeter. So 2 pi r is equal to 2 pi t square. R is 20 centimeters. Just substitute, solve it. You get a t is equal to 1.414 second. At we found it as 40 pi. We find 40 pi. So substitute the value of pi is 3.14. So you get 120.46. Velocity we got it 40 pi t. 40 pi t is 1.414. You get it as velocity 177.69 centimeter per second. Then an is v square upon rho. Substitute the value of v and r is 20 centimeters. So you get it 1578.66 centimeter per second. All right. Now next is problem number 8. A motor gives disk A an angular acceleration or that is alpha is equal to 0.6 t square plus 0.75 radian per second square. Where t is in second, if initial angular velocity of the disk omega naught is 6 radian per second, determine the magnitude of velocity and acceleration of the block B at t is equal to 2 seconds. Now, this is the diagram given to in the problem. Omega naught is 6 radian per second. Radius of this disk is given as 0.15 meter. Then it is connected, the string is wound around this disk. And at the end of this string, there is a block B is attached to it. It is turning in clockwise direction so that this block will go down only. Now, what is given? Alpha is 0.6 t square. If alpha is function of t, we'll write it definitely into alpha will it will be equated to d omega by t. So alpha is 0.6 t square plus 0.75 is equal to d omega by t. Separate omega and t terms, integrating both sides. Omega equal to is equal to 0.6 t cube by 3 plus 0.75 t plus c1. Put t is equal to 0 and omega is 6 radian per second. You'll get c1 is equal to 6. Then substitute the value c1 in the expression of omega. All right, you get omega is 0.6 t cube plus 0.75 t plus 6. Now, at t is equal to 2 seconds, we got alpha. Substitute the value of t into this expression, you get alpha at 2 seconds. Substitute the value of t into this expression, you get the value of omega. Right? As omega, as it is shown that is turning in clockwise direction, it shows that omega and alpha both will be in clockwise direction. Now, we have to understand a basic fundamental. What is that? See that this velocity of this block will be nothing but velocity of the point on the rim of the disk. All right. Acceleration of this block will be nothing but tangential acceleration of a point on the disk from where the string is unwinding from the disk. Right. So we can remember this note, velocity and acceleration of block at any instant will be equal to velocity and tangential acceleration of the point P on the disk. So velocity of this block B will be nothing but at any instant will be velocity of point P as velocity is tangential. So as it is velocity of a point on the rim will be transferred or carried forward to the string. All right. And hence the velocity of block will be velocity of point P. Now acceleration of block B will be nothing but tangential acceleration of point P. Right, because tangential acceleration will be carried forward to the string which is tangential. But as the point is if the point is on the disk, it will have two accelerations, normal and tangential. Once the point is removed of the disk, an will disappear, at will be carried forward. So now at point D, velocity of block B is nothing but velocity of point P, that is r omega. R is 0.15, omega is 9.1, that is 1.365 meter per second, and it will be vertically down. Acceleration of block B will be nothing but tangential acceleration point P, that is R alpha. R is 0.15, alpha is 3.15, 0.4725 meter per second. All right. We move to the next problem that on rotation, taken from the old Mumbai University papers. A load P is connected to a step pulley by two inextensible cables shown. The motion of the pulley is controlled by cable S, which has a constant acceleration of 250 mm per second square and initial velocity of 500 mm per second, both directed towards right, which is shown also in the diagram. Determine velocity and change in position of the load P after 3 seconds. Net acceleration of point Q on the rim of the disk. Now, students, Can you see that it says step pulley? What it is? It's a step pulley. Step pulley means a pulley with two sizes, two wheels, right? But both the wheels rotate together as one unit. Both the wheels rotate together as one unit. If the smaller wheel rotates, bigger one will also rotate. Here's given velocity and acceleration of point S. That means you are given with velocity of point Q. You are given tangential acceleration of point. Now at t is equal to 0, velocity of point S is nothing but velocity of point Q, that is equal to r omega. 500 mm per second. R is 100 radial distance of point Q from x rotation. So omega comes out to be 5 radian per second. This 5 radian per second is the initial angular velocity because it is at t is equal to 0. Now, acceleration of point S is nothing but tangential acceleration of point Q, that is equal to r alpha. It is values given to you in the problem 250 mm per second square. R is 100, so alpha comes out to be 2.5 radian per second square. He has given that acceleration of 250, what is given is constant. That means alpha will also be constant. That means the step pulley is rotating at constant angular acceleration. So at t is equal to 3 seconds, we use omega is equal to omega naught plus alpha t. Omega naught is 5, alpha is 2.5 to 3, 12.5 radian per second. Theta is equal to omega naught t plus half alpha t square. Omega naught is 5, time is 3, half alpha is 2.5 to 3 square, 26.25 radians. That is clockwise. Now velocity of block P will be velocity of point A, that is r omega. R this time I have taken bigger radius or radius of the bigger pulley. R is 200 into 12.5, that is 2500 mm per second. As this is turning in clockwise direction, so velocity of point P will be upward. Displacement of block P will be displacement of point A, that is equal to r theta. R of point A is 200. Theta we have just now find it 26.25. Substitute r 200 and theta 26.25. So you get 5250 mm upward. He is asking acceleration of point Q. This point Q at t is equal to 3 seconds. Now tangential acceleration of point Q is going to remain same. It is given, it is constant, right? AS is given 250 and it will be tangential acceleration of point Q. Whereas normal acceleration of point Q will be r omega square. R is 100 radial distance of point Q and omega after 3 seconds we found it 12.5. Substitute in that, you get 15625 mm per second square. As he is asking resultant acceleration of point Q, we need to draw a diagram. On the diagram we have shown 80 to 50 mm per second square. An is 15625 mm per second square. Resultant acceleration will like this. Beta is the inclination of the resultant acceleration with the direction of tangential acceleration. So total acceleration is 250 square plus 15625 whole square root of that. So 15627 mm per second square. Beta is tan inverse of an upon 80. An is 15625, 80 is 250. So you get beta as 89 points. So this way we have got the net acceleration of point Q on the ring after 3 seconds. We also got velocity and angular displacement of load P after 3 seconds. So this is all about, we have covered students 9 problems on the first part of this chapter, that is rotary motion. We have covered the problems of constant acceleration. We have covered one problem on motion diagram. We have covered 2-3 problems on varying acceleration also. Now we are ready to move to the next type of the problems, that is on general plane motion, which is the most important type of sums from the examination point of view. All right, so let's learn the first theoretical concepts of general plane motion. Now, we already understood this part. What is general plane motion? It is neither pure translation nor rotation. It is rather combination of the translatory motion or summation of translation and rotation. What are the examples of general plane motion? Rolling of the cylinder without slipping, rolling of the cylinder without slipping on a flat or curved surface, or we can say the motion of the wheels of the automobiles. Motion of the wheels of the automobiles on the road surface, on the roads, are example of the general plane motion. Second example, what I have given it here. Second example, a bar whose ends slide along the horizontal and vertical planes. This is right. Now, this example, we'll understand it in our next slide. Just see that. Here I have taken 2 examples I have taken. In the first example, I have taken a straight rod which is sliding, whose ends are sliding along the smooth end, a smooth horizontal and vertical plane. Can you see that this rod is initially A1, B1. After some time, it slides along the two smooth planes mutually perpendicular and it becomes A2, B2. So you can understand, you can prove that the motion of this rod from position A1, B1 to A2, B2 is example of general plane motion. How you can prove it? See, this rod was initially like this. You translate it. Translate means what? As it is, you will be pulling towards right, right? That is, so motion of the rod from A1, B1 to A2, B1 dash is translated motion. Then once you have got this position about A2, you rotate the rod. You rotate the rod about fixed axis through A2. You will get B2. So then have you got the same position or not? What you got it over here? So we can prove that general plane motion is equal to translation plus rotation. Similarly, another example, motion of a rolling cylinder on the horizontal surface without slipping. You can see that this is the cylinder which is rolling. So when it rolls, after some time, it the line A1, B1, it becomes A2, B2. Now, how you can prove that this is also example of general plane motion? First, you pull the cylinder towards right without rotation, right? So this is translating motion. And then you rotate it about A2 in clockwise direction so that you get the new position A2, B2. So here also it is justified that motion of the wheel of the automobile or motion of a rolling cylinder on the horizontal surface without slip is example of general plane motion, because we have proved that it is summation of translation and rotation. All right. Now, how we solve the problems of general plane motion? This is what we are going to learn in this part. Now, this important theory part also, many times they ask the theory questions also in the examination. What is ICR? What is instantaneous center of rotation? Well, friends, it can be shown that if you have a rigid body which is in general plane motion, at any instant it appears to rotate about some point. Next instant, the body appears to rotate about some other point. Next instant, it appears to rotate about some point. So at any instant, the point about which the body appears to rotate at that instant is called as instantaneous center of rotation. Why it is called as instantaneous center of rotation? Because the body is in general plane motion. So general plane motion is summation of translation and rotation. So this body does not rotate about fixed axis. This body appears to rotate about some point at an instant. That point is called as instantaneous center rotation. All right. And this instantaneous center rotation is always at rest. So that we also called it as instantaneous center of zero velocity. Students, using the concepts of instantaneous center rotation, we can find angular velocity of the rigid body in general plane motion. We can also find velocity of a point on the rigid body in general plane motion. How do we locate instantaneous center of rotation? Now here we come across two cases. What are the first case? Case one, you are given with the body in general plane motion, and you are given with directional velocity of the 2 points on the body in general plane motion, and they are known parallel. They are known parallel. Look at this diagram. This is the body which is in general plane motion. I have 2 points A and B on the body. Directional velocity of point A and B are given this way. Then, as you know that velocities are along the tangent, so I'll draw perpendicular to VA, I draw perpendicular to VB, where they intersect, that becomes ICR for this instant. Now, right, because this for VA velocity is along the tangent, this is normal. VB is along the tangent, normal. So two normals will intersect at point P, I is ICR. Now, looking at the directions of VA and BB, this body appears to rotate about point I in anti-clockwise direction. This body appears to rotate about point I in anti-clockwise direction. Suppose the magnitude of velocity of point A is given. So omega will be V is equal to R omega, right? Omega is equal to V upon R. So omega will be equal to VA upon AI. Angular velocity of the body is omega VA upon AI. All right. Suppose you want velocity of point P. So point P should be joined with ICR. Velocity of point P will be perpendicular to Pi in such a way that it gives anti-clockwise rotation to the body. So velocity of point P will be omega into Pi. All right. Direction of velocity of point P will be perpendicular to Pi in such a way that it gives anti-clockwise. Very important observation in the problems of general plane motion is that With reference to uh, instantaneous center rotation, velocity of all points on the body will give same kind of the rotation. Also, velocity of all points will be perpendicular to the line joining that point with ICR. As in this case, can you see that VP is perpendicular to PI, VA is perpendicular to AI, VB is perpendicular to. All right. Now we move to the second case of locating ICR. Now, here, this is the second case where direction, the velocity, the 2 points are given on the body, which is general plane motion, but they are parallel. In the previous case, they were non-parallel. Here they are parallel but unequal. First case is when they are like parallel. In the second case, velocity, the 2 points are unlike parallel. Now, how to locate ICR? Very simple in this case. Draw a line joining the extremities of the velocity vectors. Where this line intersects with the line joining the 2 points is called as ICR. You can see that we have drawn a line joining the extremities of the 2 velocity vectors. It intersects with the line joining point A and B with at I. All right. In the second case, you can see that we have drawn a line joining the extremities of the 2 velocity vectors. It intersects with the line joining those 2 points at I. So this is the way in which we locate the ICR in this case. Right. Most of our problems will be based on case 1. Few problems, the last case probably will be on second case. Now, when you are solving the problems of general plane motion by ICR method, these are some of the points which should be carefully noted. Why? These points are important. Such points are not important in any other chapter. Reason for that is ICR method is a combination of analytical and graphical method. Few steps are analytical in that, few steps are graphical into that. So you draw a diagram without adopting a scale. So there is a possibility when you are solving the problem of general plane motion by ICR method, your diagram may go out of the page. All right. To avoid that difficulty in the examination or when you are practicing the problem, you should keep in mind the following points. What I have written it. 4 points I have written it. First one, always draw line diagram. Don't need to show the thickness of the bar, all right, or thickness of the beams and all that. Diagram should not be too big or too small. Don't draw the diagram too big, otherwise also that diagram may go out of the page when you are proceeding with the solution. All right. If it's too small, you cannot show the geometry inside the diagram. Draw the diagram near the center of the page. So as far as possible, you should draw the diagram near the center of the page. Fourth, diagram should be proportional as possible in terms of angle and distance. All right. You should draw the diagram in such a way that it should be proportional in terms of distance as well as angle. So students, with these precautionary notes, I hope you all have noted these points. So keeping all these 4 points in mind, we'll start solving the problems of GPM by ICR method. You have only one method in your syllabus, that is called as ICR method. All right, there is no other method in your syllabus, right? So never get confused, because there is a method which is purely graphical method also, not in your syllabus. There is a purely analytical method also, right? Method based on kinematic relation, that is also not in your syllabus. So you will be coming across only the problems of GPM which can be solved by ICR. Let's start with the problems. Figure below shows a ladder AB 6 meter resting against a vertical wall at A and horizontal ground at B. If the end B of the ladder is pulled towards right with a constant velocity of 4 meter per second, find number 1, instantaneous center of rotation of the ladder. Number 2, angular velocity of the ladder at this instant, velocity VA of the end A of the ladder, velocity component VCX and VCY of the midpoint C of the ladder. Students, you are given with this diagram. Can you see that? This is a vertical plane. This is horizontal plane. Both the planes are smooth. This is your rod or the ladder, rather ladder of 6 meter length. C is its center point, and B is being pulled towards right with 4 meter per second. As the and B is pulled towards right, and A will slide along the vertical plane or not. It has and A, when the and B is being pulled towards right, and A is bound to follow the plane. If the plane is vertical, and A will move along the vertically down. If it is inclined, it will follow that way. Is that clear to everybody? So that means what we can say that at this instant, velocity of point B is towards right by 4 meters second. Velocity of point A will be vertically down. So we draw a line diagram as I discussed. I have drawn X and Y lines. I have drawn the rod. Right here we should make sure that this 30-degree angle should be at least less than 45. When you are drawing the diagram, make sure that this angle 30 degrees should be lesser than 45. And B is being pulled towards right with 4 meters per second. And A will go down with velocity. Draw perpendicular to BA, draw perpendicular to BB. You got ICR. All right. Now in triangle ABI, this is 30, this is 60. So what you can get it, length AB 6 meter. So BI is 6 cos 60. That is 3 meter. A distance AI is equal to AB sine 60. What is that is 6 sine 60, 5.196 meter. Now I is ICR. Keep your pen or pencil at the point I to create axis rotation. Look at the direction of VB. Ladder appears to rotate in anti-clockwise direction or not. So omega of the rod is equal, ladder is equal to VB upon VI. Omega of this ladder is VB upon VI. VB is 4, VI is 3, so 1.33 radian per second in anti-clockwise direction. How do you understand anti-clockwise? Once again, I repeat, keep your pen or pencil at I. Look at the direction of VB. You'll find that ladder appears to rotate in anti-clockwise direction based on direction of VB. As VB is giving anti-clockwise rotation, so VA should also give anti-clockwise rotation. It is giving since it is downward. All right. And so downward with respect to I, it gives anti-clockwise. So that is correct. How you find VA? Omega into AI. Right? VA is omega into A. Omega is 1.333. AI is 5.196. You get 6.926 meter per second vertically down. Now, he is asking velocity components of velocity of point C. Right? VCX and VCI. So first we have to find VC. How will you find VC? Point C should be joined with ICR. Point C should be joined with ICR. Velocity of point C will be perpendicular to CI in such a way that it gives anti-clockwise rotation with respect to axis rotation through I. You can see if your pencil is kept at I, you can see that VC will be perpendicular to CI so as to give anti-clockwise rotation. You can also check that if you have kept your pencil at I, you can see that VB, VC, VA are giving anti-clockwise rotation only. All points should give anti-clockwise rotation. Now, to get the velocity of point C, you need to find distance CI. This is 60, this is 3 meter, this is 3 meter. So initially we understand that it is isosceles triangle, but then since this is 3, this is 3, this is 60. Sum of these two angles is 120. So 120 divided by 2, as these two angles will be equal, is 60. So we understand that triangle BCI is equilateral triangle. We understand that triangle BCI is equilateral triangle. Since triangle BCI is equilateral triangle, CI is also equal to 3 meter. So we understand that CI is equal to 3 meter. So velocity of point C is omega into CI. Omega is 1.33 into 3, 4 meter per second. Now, what angle it makes with x-axis? Look at the diagram here. Look at the diagram here. What do you find that? See, this is 60, this is 60, this is 60. If you draw a x line through C, you draw the x line through C, this angle is 30. This is 30. This angle is 30. So we can say this angle is 30 degree as alternate angle. Now this angle is 60, so this has to be 30. All right. I repeat again, angle ICB is 60. You draw X line through C, you'll understand that this angle is 30. How this angle is 30? As alternate angle of this. Then this VC is perpendicular to CI. So this angle is 30. How do you understand this angle 30? 90 minus 60, that is 30. All right. So we understand that VC is making 30 plus 60, 60 degree. We have marked it. All right. Then VCX will be 4 cos 60 to the right. That is 2 meter per second. VCY will be 4 sin 60, 3.464 meter per second. That is what it is. Now, this is observational part which I have written as a note. It should be noted that velocity all points on the body in GPM will give same type of the rotation about ICR. Right? Example, in the previous problem, VA, VB, VC are giving anti-clockwise rotation about I. I think we have already discussed this point with respect to axis rotation through I. VA, VB, and VC all are giving anti-clockwise rotation to the body. Also, velocity of all points on the body will be perpendicular to the line joining that point with ICR. You can say VA is perpendicular to AI, VB is perpendicular to BI, VC is perpendicular to CI. Let's move to the Next sum. That's it. Problem number 2. Using instantaneous center rotation, that is ICR method, find the velocity of point A for the instant shown in the figure. Collar B moves along the vertical rod, where link AB moves along the plane, which is inclined at 25. Students, you don't need to draw the given diagram as it is. What we do that? We draw a diagram where we show this inclined plane and this. This is 25 degree, it is given here. Okay. We draw the bar of length 1.2 meter. Okay. The purpose of connecting this rod to this collar, which is moving vertically up along 1.5 meter, is this collar is bound to move along this vertical rod or guide. Collar at B is bound to move vertically up only with velocity 1.5. That means we can say that velocity of point B is 1.5 meter per second upward. So we have shown velocity of point B is 1.5 meter per second upward. When the collar is being pulled up, and A will slide up along the plane. When the collar B is going up, and A will slide up the plane. So and A will slide up the plane, that is velocity of point A. Draw perpendicular to VA and perpendicular to you located ICR. Now this angle is given to is 45. This angle is 90. So what is this angle total? 45. This total angle is 45. This angle is 25. So this angle is 20. Can you see that? Again, I repeat. In this right angle triangle, this is 45. This is 90. This total angle, this one, is going to be what? 45. This is given to is 25. Plane is inclined at 25 degree horizontal. So the bar will be making 20 degree with the plane. So this angle 20. This line is perpendicular to plane. So this angle will be 70 degree. 90 minus 27. This is 45. So this angle is again 45 because we have drawn BI perpendicular to VB. This is 45. This is 70. 45 plus 70 is 115. Right? This angle will be then 180 minus 45 minus 70. That comes out to 65. Then in this triangle ABI, we can apply sine rule. When we apply sine rule, 1.2 upon sine 65, BI upon sine 70, AI upon sine 45. This is what we have done it, students. Now you use the sine rule, you get it AI and BI. Now keep your pen or pencil at I. Your VB is given to you. Look at the VB. With respect to axial rotation through I, VB gives the anti-clockwise rotation to the body about axial rotation through I. Again, I repeat, keep your pen or pencil at I. Look at the direction of VB. You will understand that this rod appears to rotate about axial rotation through I anti-clockwise. So we understand that omega is equal to VB upon VI. VB is 1.5. VI, we got it 1.244. So you got omega, angular velocity of this rod, right? This link AB in anti-clockwise. You want velocity of point E. Velocity of point A is omega into AI. Omega is 1.206. AI is 0.936. You get 1.129. What is the inclination of the velocity? As velocity of point A is along the plane, which is making 25 degree with the horizon. All right. This is what this type is quite important from the examination point of view. All right. That's why I'm covering 4 problems on type 1 itself. Okay. I read third sum of the type. Rod AB of length 3 meter is kept on the smooth plane as shown in the figure. Velocity of end is 5 meter per second downward along the inclined plane. Velocity of end A is downward along the plane 5 meter per second. All right. Locate the ICR and find the velocity of end B. Student, we'll draw the line diagram as you have shown this plane 30 degree. You have shown this horizontal plane. And A of the rod and A of this rod is velocity is 5 meter per second down the plane. When and A is being pushed down along the plane, right, and B will move towards right along the plane or not. So velocity of point B will be horizontally or towards right along the plane. As the plane is horizontal, velocity of point B will be along the plane, so that is horizontal. Draw perpendicular to VA, draw perpendicular to VB. This problem is almost identical to what we did in the previous one. Now student, this angle is 30 degree. So 180 minus 30, this angle is 150 degree. This is 20 degree. All right. So this angle is 70, 90 minus. Now you can understand that this is 10 degree. How you got this 10 degree? 180 minus 20 minus 150, you get 10. This is AI is perpendicular to this plane. So 90 minus 10 is 10 degree. You got this as 10, 80. You got this as 70. So you get this angle as 180 minus 70 minus 80. That is 30. So this way, all the three angles of triangle ABI are arrived at. Then again, we use sine rule as we used in the previous problem. How come? Just see that again. Using sine rule, you'll get it AB 3 upon sine 30, BI upon sine 80, AI upon sine 70. So you get AI and BI. Now keep your pen or pencil at I. Look at the direction of VA because VA is given, right? What is given? First we look at it. So you'll find that this rod appears to rotate in anti-clockwise direction. So what will be omega? VA upon AI. Omega is angular velocity of this rod. VA upon AI. All right. VA is 5. AI distance, we found it as 5.68. So angular velocity of the rod AB is 0.887. You want to find angular linear velocity of point B of the rod. VB will be omega into BI. Omega is 0.887, BI is 5.9. You get 5.241 meter. Problem is over. At this stage, we have got angular velocity of this rod AB. We have got velocity of point B. Velocity of point B will be towards right. This is correct. Why it is correct? If you keep your pen or pencil at I, you saw that VA was giving anti-clockwise rotation. Even VB is also giving anti-clockwise rotation. We know that velocity of all the points on the body in GPM should give same kind of the rotation. As VA is giving anti-clockwise rotation with respect to X rotation through I, VB is also giving anti-clockwise rotation with respect to the axis through I. Now, students, sine rule application is quite common in engineering, right? Cosine rule application is also there, but not that common. So cosine rule, I'm discussing how we will use it in this chapter and in what situation we come across the use of cosine. Now students, cosine rule, we have drawn a triangle. Three sides are ABC. We learned that we at cos theta is equal to A square plus B square minus C square upon 2AB. Normally, when do we use cosine rule in this chapter? When in a triangle, two adjacent sides are given, included angle is given, opposite side is required, we use cosine rule. So I'm rearranging the terms in this expression. So C will be equal to square root of A square plus B square minus 2AB cos theta. So in this chapter, we will use cosine rule in triangle when the two adjacent sides and included angle between them are given and opposite side is required. We should use cosine rule, preferably in the modified format. What is the advantage in modified format? You can, it is easy to use the calculator for finding C. So we'll remember it like this. In a triangle, if two adjacent sides are given, included angle is given, opposite side is required, we go for cosine. Now we move to the problem on cosine rule based working. I'm reading the sum. This again only our type 1 fourth problem. Read it. Rod ABD is guided by the wheels at A and B, which rolls in horizontal and vertical tracks as shown. Knowing that beta is 60 degree and the wheels at A moves to the left with the constant velocity of 30 centimeter per second. Determine the velocity of point. Now look at the diagram, students. Here this is your rod ABD. It is one piece, all right, and A of the rod is connected to a roller or a wheel which slides in a horizontal, and A of the rod is connected to a wheel which slides in a horizontal track. That means at any circumstance, under any circumstance, velocity of the point A will be horizontal. This is the concept part. Now we come to point B on the rod. Point B on the rod is connected to a wheel again. Wheel moves in a vertical track. That means velocity of point B will be vertical. So by looking at the diagram only, it should come to our mind that velocity of point A is horizontal and velocity of point B is vertical. Is that clear to everybody? Now he says that and A is being pulled towards the left with the constant velocity of 30 centimeters. That means velocity of point A is 30 centimeters per second towards. Now draw a diagram. We have drawn the rod AD of length 30 centimeters. B is the midpoint of it. And A is being pulled towards left with 30 centimeters per second. If and A is being pulled towards right, velocity of the point B, which has to be vertical, will be vertically down as it tends to go down. Draw perpendicular to VA, draw perpendicular to VB, you get instantaneous center of rotation. Then in triangle ABI, you get the two sides. AB is given to 15, this angle is given to 60. How do you understand this angle is given as 60? It is given in the diagram. Beta is given to you as 60 degree. This 60 is given. So AI is going to be adjacent, 15 cos 60. BI is going to be opposite, 15 sin 60. Got AI. Now keep your pen or pencil at I. Look at VA. This rod appears to rotate in clockwise direction. So angular velocity of the rod, say omega, will be equal to VA upon A. Omega is VA upon VA is 30. AI is 7.5. We got 4 radian per second clockwise. You want to find velocity of point B? No, he's not asking. He's asking velocity of point B. But if you keep your pen or pencil at I, you see that VA was giving clockwise rotation. So VB is also giving clockwise rotation. That means direction of VB was correct. Then you want to find velocity of point D. How do you get velocity of point D? Point D should be joined with ICR. Velocity of point D will be perpendicular to DI in such a way that it gives clockwise rotation with respect to axis through I. You can see that if you keep a pen or pencil at I, BD is perpendicular to DI in such a way that it gives clockwise rotation. BD is omega into DI. BD is what? Omega into DI. But then DI distance is required to me. How will you get distance DI? Now, in triangle BDI, can you use cosine rule or not? This is 15 centimeter. This is given to you as 13 centimeter. Included angle is given. In triangle BDI, DI is required. You have two adjacent sides of a triangle are known. Included angle is known. Opposite side is required. So use cosine rule. DI is equal to BD square plus BI square minus 2 into BD into BI into cos 150. Substitute the value of BD as 15 and BI as 12.99. 12.99 or even 13 also you can write. You got DI as 27.04 centimeters. So what is VD is equal to omega into DI. All right. We have found it. Omega is 4, DI is 27.108.16. Then question comes, at what angle BD is acting? Now this DI is making angle theta with horizontal. As you can see in the this triangle, DI is making angle theta with horizontal. This. So VD will make angle theta with vertical. Our standard geometrical note, what we learned in statics in many problems. Plane or line is making angle theta with horizontal. Any line or force normal to that plane will make theta with vertical. So in this triangle BDI, how you can get angle theta? You can use sine rule. 15 upon sine theta is equal to DI upon sine 150. We applied sine rule. BD upon sine theta, DI upon sine 150. BD is 15 upon sine theta. 27.04 upon sine 150. That. So again I repeat, since DI is making angle theta with horizontal, BD will make angle theta with vertical. Students, in this lecture, that is my today's lecture, I have covered 9 problems on rotation, right? Whether rotation of at constant acceleration, varying acceleration, and motion diagram. Then we came on general plane motion. In general plane motion, we understood the theoretical concepts of ICR. We understood that 2 types of the cases of ICR we come across. We have taken up 4 problems on type 1, that is single bar in GPM. We will be having 5 more types of the problems on GPM. All the problems are going to be important. All types are important. We need to understand the different types of the problems also, so that in the examination, they will not give you that which type of the problem it is. It is given to you only a problem. So by looking at the problem, you should understand that whether it belongs to type 1, type 2, type 3, type 4, or type 5, or type 6. All that will come to your understanding once all other 5 types are covered. So in my next lecture, I'll be covering 5 more types of the problems on GPM, right? The more solved problems or some practice problems, multiple choice questions, and etc. You can come across if you refer to my problems on engineering mechanics, which is available at local bookstores as well as on Amazon. On Amazon, we have arranged for some discount as well as free delivery. Link of Amazon is given in the video description of this lecture. Right, students, these video lectures are completely free. You can share the QR code with your friends. Please help your friends in learning mechanics without joining any tuition classes. All right, you can share this QR code so everybody can get the access to my free video lectures. Right, it will benefit a lot to them. Even if they don't buy the books, still they can be. I have designed my lectures in such a way that even if you don't buy the book, still you will have the understanding about the subject. Okay, thank you.